Hey everybody, welcome to this special makeup lecture. This is part 1 of 2, focusing on the properties of solids. And because this is a double header, grab your coffee, let's get going. We left off talking about silicon versus aluminum nitride. And this is a really interesting comparison because silicon and aluminum nitride have the same number of valence electrons. Silicon has 4 each, whereas nitrogen, one column to the right, has 5, and aluminum, one column to the left of silicon, has 3. That gives us a total of 8 valence electrons for the molecule Si2 as well as for the molecule Aln. And placing these electrons in, we find that in both cases we completely fill up the bonding molecular orbitals, and the anti-bonding ones, the 4 at the top, are completely empty. We then have this thought process of extrapolating this result into a solid material with an infinite number of atoms. When we do that, we get bands, our valence band and our conduction band. So the valence band is made completely from these filled molecular orbitals, and the conduction band is made entirely from the empty molecular orbitals. Okay, so silicon and aluminum nitride in some ways look very similar, but there's one important difference. And that important difference is that the aluminum is more electropositive than silicon, and nitrogen is more electronegative than silicon. So that shifts those two orbitals, aluminum higher in energy, less stable, nitrogen lower in energy, more stable. And the consequence of those shifts in the orbital energies is in shifting the aluminum energies up in energy, it also shifts the resulting molecular orbitals up in energy. When we shift the nitrogen down in energy, it shifts these filled bonding molecular orbitals down in energy. If we shifted the top ones up in energy and the bottom ones down in energy, that naturally means that there is a larger gap between the filled states and the empty states. Okay, so now when we take these MO pictures and we extrapolate these energies into bands, so this is our filled valence band, and this is our empty conduction band in silicon, we have a small-ish band gap of 1.1 electron volts. When we do the same process in aluminum nitride, here is our filled valence band, and here is our empty conduction band. And because that aluminum was higher in energy and nitrogen was lower in energy, our resulting valence band is also lower in energy, and our conduction band is higher in energy. And the consequence is that we have a larger band gap in aluminum nitride. When we actually look at this material, aluminum nitride, it's a white material, meaning that it has such a large band gap that it does not absorb visible light. And in general, that's what we can infer from seeing a white material, is that it has a large band gap. It's not absorbing visible light. Silicon, in contrast, has a smaller band gap and is able to absorb all colors of visible light, red, green, blue, ultraviolet, even a little bit of infrared light, and therefore it is a black material. So this very simple difference between silicon and aluminum nitride, where because aluminum is more electropositive, nitrogen is more electronegative, that shifts our valence band down, our conduction band up, and turns it from a material being black into a material being white. That band gap is so large in aluminum nitride that we would call this an insulator. And of course, we've said that silicon is a semiconductor, and aluminum nitride is a insulator because it takes more energy to excite an electron from that valence band up into the conduction band. It takes more energy than in silicon. So silicon is going to be more conductive. Aluminum nitride is less conductive, and that's why we call aluminum nitride a insulator. Okay, so let's do some comparisons now. What is the band gap of aluminum phosphide? And let's just take a quick look at our answers here. So we could have a possibility of it being smaller than silicon. It could be larger than silicon but smaller than aluminum nitride. Or it could be larger than aluminum nitride. Okay, and for convenience, I've depicted both the silicon molecular orbitals as well as the aluminum nitride molecular orbitals. Okay, pause the video, work through this problem. Okay, so when we replace nitrogen for phosphorus, phosphorus has the same number of valence electrons as nitrogen. That means that the aluminum phosphide molecule has 8 valence electrons. And just for convenience, I'm not drawing them as arrows, just as little tick lines. Okay, so, but here's the one difference. Is phosphorus more electronegative or less electronegative than nitrogen? Okay, so we move down on the periodic table. Those electrons are held less tightly than in nitrogen. Phosphorus is less electronegative than nitrogen, and that shifts these energies up ever so slightly. In shifting up those energies, we also are going to shift these energies up slightly as well. The consequence is that our new band gap, and I'm drawing this on the molecular orbital. The molecule does not have a band gap, but I'm just kind of showing this schematically. Our new band gap is going to be smaller than aluminum nitride, and larger than silicon. It's larger than silicon because aluminum is more electropositive than silicon, and phosphorus is more electronegative than silicon. So we can then just use those electronegativities to say, okay, that difference in electronegativity for aluminum phosphide is between the difference in silicon, 0, and the difference in aluminum nitride. So our answer is therefore that aluminum phosphide falls right in between those two. Okay, now the valence band in aluminum phosphide. Okay, so what is the valence band? Which orbitals are making up the valence band in aluminum phosphide? Pause your video, think through this, and restart it when you're ready. We've said before that the valence band is made primarily from orbitals that are closest in energy, if we're doing our band diagram for, or rather our MO diagram, we will see, of course, that because phosphorus is lower in energy, phosphorus is going to be closer in energy. Yep. Sorry, not thinking through this carefully. Let me correct that. Okay, so, and we can put in our electrons. Okay, so we've said that the valence band is made primarily from those orbitals closest in energy. That's clearly going to be because these states give rise to our valence band. We can therefore predict that the valence band is going to be made mostly from phosphorus. It's not made only from phosphorus, because we do know that aluminum and phosphorus, those orbitals, do mix together to make those bonding molecular orbitals. So there's some interaction between them. So there is some amount of contribution from aluminum. It's just smaller than the contribution from phosphorus. So that's why we say it's not only phosphorus orbitals. And those contributions are not equal either. So we would say our valence band is made mostly from phosphorus. Okay? And that makes sense because we know that aluminum is more electropositive, phosphorus is more electronegative, so we would expect some amount of electron donation from aluminum to phosphorus. Hence, the phosphorus is going to have extra electrons. And that's exactly what we see in our valence band picture, is that this valence band, which is made mostly from phosphorus orbitals, is occupied with electrons. In contrast, the aluminum is not occupied. So these these states which give rise to our conduction band, these states are empty, and these states are made more from aluminum than from phosphorus. So if we were to ask you the opposite question, the conduction band is made mostly of what? You would say the conduction band is made mostly from aluminum orbitals, because aluminum is closer in energy. Okay. Okay. Okay, another related question. So what's the band gap of boron phosphide, BP? Okay. And now we can compare the band gap of boron phosphide to silicon, aluminum phosphide, and aluminum nitride. Okay. Boron, pause your video, solve it. Okay. So boron, is that going to be more electropositive or more electronegative than aluminum? So we know that as we move up on the periodic table, the atoms become more electronegative. So boron is going to be more electronegative than aluminum. That is going to shift our states down a little bit. So if we were to depict this one, we've shifted those states of boron down, and our phosphorus is going to be shifted a little bit up relative to nitrogen. Okay. So now when we build our molecular orbital with our bonding set and our anti-bonding set, we get something that looks like this. And the great thing about this example is that the electron count is exactly the same as before. Boron, like aluminum, has 3 valence electrons. So putting those in, 1, 2, 3, 4, 5. And so we have 8 valence electrons total. This is completely filled. The bonding states are completely filled. And that gives rise, again, to our valence band, which is completely filled. And, of course, our conduction band, which is completely empty. Okay, so that's filled. Okay, so we can see that compared to aluminum phosphide, boron phosphide is going to have a smaller band gap because boron is less electropositive, more electronegative than aluminum is. So that conduction band shifts down in energy. The result is the band gap is smaller than aluminum phosphide. So we can cross out C and D as possibilities. Okay, so is boron phosphide smaller than silicon or larger than silicon? It's going to be larger than silicon because compared to silicon, the boron is shifted up in energy and the phosphorus is shifted down in energy. So that gives rise to a larger band gap. Okay. So B is correct. Okay. Okay, so to summarize this, we've seen a number of important principles. First one is that whenever we're combining 2 orbitals together, like 2 s orbitals, they form that bonding sigma orbital and an anti-bonding sigma star orbital. Same idea for other orbitals, but we've kind of skimmed through those details. And we're not expecting you to know the fine details of what happens when p orbitals combine, for example. Just know that you should expect they will form a bonding and an anti-bonding combination. These plots of MO diagrams, the vertical axis is energy. That means that we are going to put electrons into the energy levels at the bottom, that's the lowest energy, and work our way up, because if given the option, electrons are going to go into the lowest energy, most stable molecular orbitals, or they'll go into the most stable, lowest energy states in the solid. We've seen the principle that the number of molecular orbitals, or states, equals the number of atomic orbitals used to build that system. We saw that specifically in the case of hydrogen, where we had H2 that had a bonding and an anti-bonding MO. We had H3 that had 3 MOs. We did H4, which had 4 MOs. H infinity had an infinite number of MOs, which, because we get tired of drawing all of these lines representing MOs, we just draw them as a band, which represents an infinite number of states. And those states are spaced infinitesimally close to each other, so that there's a whole range of energies that can potentially be occupied by electrons. That's how we get our valence band and our conduction band in these solids. We've seen the idea that partially filled bands give rise to metals. I think that idea we've hit on a number of times now. I won't explain that further. For semiconductors and insulators, we have bands that are completely filled and bands that are completely empty, but no partially filled bands. And we've also seen now, most recently, the principle that the larger the difference in electronegativity of two atoms, the larger its band gap. And that's a really cool idea because, like in the case of aluminum nitride, we can think of aluminum nitride as being an insulator because of its large band gap. And that's exactly what we would predict, that aluminum nitride is an ionic solid in which the aluminum has given its electrons to the nitrogen. So we would think of that as aluminum 3+, nitrogen 3- in terms of ionic solids. And we know that ionic solids are poor conductors. So that connects our ideas from earlier about, ionic solids are poor conductors, and connects them to what we see as a prediction out of MO and band theory. Okay. The last little topic that we'll talk about in terms of solids is nanomaterials and quantum confinement. It's a really cool concept. We have a really different way to tune the band gap or the color of a solid. Before, we saw that we could tune the band gap by changing the composition from silicon to aluminum nitride to aluminum phosphide, or not necessarily in that sequence, but now we have a different strategy. We can use this effect called quantum confinement to change the band gap, and that ends up being really important for applications where certain applications we want to have a band gap of a very specific size, such as in a solar cell. We would want the band gap large enough so that that excited electron has a lot of energy to do work, but we would want the band gap small enough so that we can absorb many wavelengths of light. So there's a in a solar cell, there's a specific band gap that's optimal for maximizing efficiency. Tuning the band gap through quantum confinement gives us a set of tools to achieve that increase in efficiency. Light-emitting diodes are another application where rather than absorbing light, we want to emit light. And as you know, the color of light that might be emitted from a light can be subtly different. Oh, this light is really blue, looks bad. Oh, this light is, a little bit warmer, more orange or red, more pleasing. So that balance of color in emitted light is really important for applications. And light-emitting diodes, which are a much more efficient way of producing light in homes, is a technology that requires the emission of red, green, and blue light in exactly the right proportions to have that desired color balance. So, and of course, computer displays, which emit light of various colors, are also another application for these materials that can potentially emit light of very specific colors. Okay, so how does quantum confinement work? Well, the basic idea is when orbitals overlap, that can allow the electrons to be shared. And when the electrons are shared among orbitals, we say that those electrons are delocalized. So I want you to picture 3 different chains of hydrogen atoms and select which one the electrons are best shared in or best delocalized in. Okay, so you should have selected C, because in the case for A, we just have a bunch of independent orbitals that are not even really physically touching. The electrons are going to have a very difficult time moving from orbital to orbital because the orbitals are not in contact with each other. So C gives us the best overlap. The more orbital overlap we have, the more readily electrons can be shared among atoms. So, and using this terminology, we would say that electrons are the most delocalized in case C. That idea actually allows us to begin talking about the size of an electron, and this is kind of a nebulous concept, because that electron, we talk about this as a probability distribution. That is, if we're representing this as our electron cloud here, that we would say the probability of finding an electron might be highest where we've shaded it the darkest, and it's a little bit lower in the, farther out, and even a little bit lower even farther out. And so what we're describing when we talk about the size is that probability distribution for that electron. But the key idea is that as orbitals overlap more, those electrons are going to be shared better, and they're going to simultaneously exist on several atoms. That means, and to say that more specifically, that probability distribution is going to extend across a larger number of atoms. So if we were to depict these two cases, a string of hydrogen atoms, one with a small spacing, one with a large spacing, we could have a slightly smaller cloud that represents that probability distribution. So it's going to be smaller when the orbital overlap is worse. Okay, so the thing that's really remarkable is that some materials share electrons so well that they will have a probability of existing on many thousands of atoms simultaneously. So you could think of that as essentially saying the electron has a physical size that extends over thousands of atoms. And one example, in cadmium sulfide, a single electron can be shared by about 10,000 atoms simultaneously. To say that more precisely, it means that if we were to ask the question, where is the electron on cadmium, on this cadmium sulfide, there would be some probability of finding that electron on any one of those 10,000 atoms if we were to look for it. So that probability distribution spans across a large number of atoms, like 10,000. Okay, so now what happens if we make really small particles? If we make really small particles that contain fewer than 10,000 atoms, that electron is not going to like it. It's, that electron wanted to exist across many atoms, 10,000, but now there aren't that many. So that electron is going to be confined. We would say then, if we confine that electron, we are going to destabilize that electron. And the way that we think about this is specifically in terms of the electron that is in the conduction band. So when we take light and we excite an electron from the valence band up to the conduction band, that electron in the conduction band we will talk about now as, say, having that physical size that allows it to be shared by 10,000 atoms. But wait, it can't. it's on too small of a particle, it's confined. And that change in the size from the ideal size destabilizes that electron and makes it go up in energy, or makes the conduction band as a whole go up in energy. So the effect is, as the particle becomes smaller and smaller, the quantum dot becomes more and more confined, or the electron becomes more and more confined, and the band gap gets larger and larger because that electron in the conduction band becomes less and less stable. So that's what this picture is showing, going from left to right. As the particle becomes smaller, electrons become more confined. And as the confinement increases, that electron in the conduction band becomes more and more unstable, meaning it shifts up in energy. Therefore, the band gap, that energy difference between the valence band and conduction band, it increases. That's it. That's the idea of quantum confinement. It's, in some ways, a pretty cool effect, because just by changing the size of the object, you can have an incredible change in the material's colors. Okay, so and there's many ways that you can even implement quantum confinement. You can implement quantum confinement as a quantum dot. So this would represent a particle where all that particle is giving us electrons that are confined in all three dimensions, x, y, and z. We could also have an object known as a quantum wire, in which we are only confining electrons, let's say, in these two dimensions. Maybe we would call them x and y, but the electrons are not confined in z. We can have a quantum well, which only has one small dimension and confines the electrons only in that dimension. And then, of course, we have a material like a bulk semiconductor that has an infinite number of infinite number of atoms, and has no confinement at all. Okay, so quantum wells, quantum wires, quantum dots are three different ways that we can achieve quantum confinement. It gives rise to slightly different properties in each case, but the key idea for all of them is that the smaller you make the object, for the quantum dot, the smaller its diameter. For the quantum wire, the smaller its diameter. The quantum well, the smaller its thickness, the larger the band gap will become. And this effect then allows us to tune colors really widely. So in this example of a quantum dot, this could represent, for example, cadmium selenide, a common quantum dot material. 6 nanometers gives us red particles. As we go down to the 2 nanometer particles, they become blue. And anywhere in between, you can shift the color from yellow, green, cyan to blue. And the corresponding picture is we have our valence band in red, our conduction band empty in blue, and that band gap, the energy difference between the valence band and conduction band, is getting larger and larger as we move from left to right. It's a pretty cool effect. And these materials are just beautiful. So this is a photograph on the top left of quantum dot solutions. The reason that they appear to be glowing is because they are glowing. In this photograph, the person setting up this picture is shining ultraviolet light on the quantum dots. That ultraviolet light is larger in energy than the band gap in any of these quantum dots. Therefore, the ultraviolet light is being absorbed. Then that light that ultraviolet light, when it's absorbed, creates an excited electron. So we might excite an electron up to a high energy level in that quantum dot. Then, through a series of quick relaxation processes, that electron falls back down to the bottom of our conduction band. So here's our valence band down here. So these small relaxation processes happen really quickly and occur by just the emission of a little bit of heat. Okay, so that happens quickly. The electron then stays there at the bottom of the conduction band, and then eventually there's some probability that the electron falls back down to the valence band, and when it does that, it emits a photon, light, and it emits a photon of light that has an energy equal to the energy of the band gap. So if we had a band gap, E gap, of 1.8 electron volts, then it would emit red light, for example. And so that's the case on maybe these quantum dots on the far right. So again, this experiment is we shine ultraviolet light on the quantum dots. We excite electrons up to the conduction band, maybe to some high state in the conduction band. Those electrons kind of relax back down to the very edge of the conduction band. As they do that, they give off a little bit of heat because we have to conserve energy. And then in one fell swoop, the electron hops down to the valence band, emitting a photon of light that's equal to the band gap energy. And in that way, because we've tuned the band gap across these series of quantum dots with slightly different sizes, they give off colors of slightly different wavelengths, or very different wavelengths. So we go from the beautiful violet colored emission to the beautiful red colored emission in these quantum dots. That's how the quantum dots can be tuned to either absorb different wavelengths of light or emit different wavelengths of light. And that's what happens in technologies now like quantum dot TVs or quantum dot computer monitors. So those quantum dots are in the TVs and monitors emitting these really well calibrated colors of light to, for example, in a monitor, emitting red, green, and blue lights in different proportions to, meet the expectations of the viewer. Okay, so looking forward, there's a whole variety of future possibilities for quantum dot materials for potential use in solar cells, and they are attractive for use in solar cells as well as other technologies because of their tunable light absorption properties, and they can be tuned across many different sizes using different semiconductors. So we've talked about cadmium sulfide and cadmium selenide, but there's many other compositions that are going to have different degrees of tunability. We can get quantum dots that are tunable more in the IR. We can get them that are more tunable in the ultraviolet. And so there are countless really interesting possibilities for tuning the optical properties for specific applications through not just changing the chemistry, but changing the size. And that's quantum confinement. And a picture of a quantum dot solar cell with those quantum dots in it representing here there's a physical quantum dot and then some organic molecules that are coating the surface of the dot, keeping them physically separated from their neighbors so that they maintain their separation and maintain their quantum confinement even when they're packed into a solid film as they would be in a solar cell. All right, that concludes the presentation of part 1. Take a sip of coffee, continue part 2.